So once you've downloaded the material for today's workshop, the first step is to import your workflow or the workflows which we prepared into KNIME Analytics platform. What you have to do therefore is to go to the KNIME Explorer, which is on the upper left, and you can right-click on Local, and then select Import KNIME Workflow. This will open a new window for you, and if you click now on the Browse button, then you can just browse to the location where you have your downloaded files, probably your downloads folder, and then select the file learnathon _2020.nar and select Open. And then you should be able to click here on Finish. I can't do this because I have imported it already. And once you have done this, you will see here in the KNIME Explorer a folder, this is something what we call workflow groups, which is called Learnathon 2020. And if you click now on this triangle in the front of it, then we can see the subfolders or the other workflow groups. And our workflows are in the folder Challenges, Group 2, Training, Evaluation and Optimization. And we will use the workflow Group 2_1_ Training, Evaluation and Optimization. And to open the workflow, I can just double-click on this workflow here. What we see here now are many meta nodes. So inside, we can have multiple nodes. And we have here one meta node, which is called Data Access Cleaning and Partitioning. And in there, so if I double-click, it opens a new tab, and we can see the nodes, which are hidden in there. We can see what group 1 is going to work on, because what this group is going to do is it's going to read the data and pre-process the data for us so that we have here at our output ports a training data set and a test data set. Let's have a quick look at the data which we want to use. So we have two data tables. We have on one hand the information about the different flights. And one of the columns is the departure delay column, where we have the departure delay in minutes. And on the other hand, we have also some weather information from Chicago. Then we have here the data preparation meta node. Here we, for example, filter only the flights from Chicago, and we use the rule engine node to actually create a column with our class information, whether a flight is delayed or not, depending on whether this flight had more or less than 15 minutes departure delay. And the last step that we do, this meta node does, or the workflow does in this meta node, is that we filter out columns with the information which we don't know before the airplane has started or landed, which is, for example, the arrival delay, the departure delay. So we remove all of these columns. Okay, but as I said, this is what Group 1 is going to work on, and Paolo will record his session as well. So if you are interested in how you can solve the exercise of Group 1, this will be available on YouTube afterwards as well. But let's now focus on training a machine learning model. And therefore, I will first use this decision tree meta node here. A quick side note, for the second node here, we have a small typo. This shouldn't be linear regression, but logistic regression. But we will come back to this meta node in a few minutes. So let's start with our exercise and train our first model to predict the departure delay, a decision tree. And therefore, I go inside of this meta node by double-clicking on this meta node. And by double-clicking on this meta node, we get here a new tab. And we have here an annotation box which tells us what we are supposed to do. And the first thing we want to do is to train a decision tree to predict whether a flight is going to have a departure delay or not. And I will increase this a bit for you. Here we go. And for all the algorithms which we have in KNIME Analytics platform, we have always a learner node and a predictor node. And we can use the learner node to train the model and then the predictor node to apply the model. So the first thing I will do is I will go to the node repository, which is here on the lower left, and I will look for the decision tree learner node. So let's look for the decision tree learner node in the node repository. Here I have the decision tree learner node, and I can create a decision tree learner node or a node by just dragging and dropping it from the node repository to the workflow editor. Then I feed my training data, which I want to use to train my model, into the decision tree learner node. And then I can open the configuration window to define the algorithm settings. to open the configuration window, I just double click on this decision tree learner node, and this opens the configuration window for me. Here we have now different settings options. The most important one for now is the class column, where we define in which column do we have our class information for the model which we want to learn. And KNIME did set this setting already correctly, which is the departure delay. Next, we have different setting options for the decision tree algorithm. The idea behind the decision tree is that it always splits the data set into multiple subsets based on one of the input features to find pure subsets. And it always takes the feature which leads to the purest subsets as the splitting feature. And to decide which is the best feature, we have different quality measures. And here we can choose between two quality measures, either the Gini index or the gain ratio. Then we have some more setting options for the decision tree learner node, which help us to handle overfitting. And here we have to handle overfitting in the decision tree algorithm, we have two options. We can either use early stopping or we can use pruning. Early stopping would mean that we don't allow the algorithm to grow a really deep tree. And the idea of pruning is that we first grow a really deep tree, and then we cut branches, which seems of a result of overfitting. To use early stopping, you can increase here this number of minimum records per node. This number defines when the algorithm stops to split. So here if we set 2, then it splits until we have only 2 samples in a subset, or the subset is pure. So if we increase this number here, we will get a shallower tree, which is not so deep. And then for pruning, we have also two options. We can use reduced error pruning, and we have here in addition also the option to use minimum description length pruning. The other option that we have here is to skip nominal columns without domain information. That's something I want to do now because we have some columns where we miss the domain information, where we have too many different values. But besides this, I will go for now with the default settings, and we will later on change a few of these settings. Then I can execute the node by right-clicking and select execute. If you have any questions regarding what I'm showing now, or if I'm too fast and you want to see a configuration window again, feel free to let me know in the chat. I will check the chat regularly, and I'm happy to show you configuration windows again. Now that we have executed the decision tree learner node, we have now here our decision tree at the output port, and we can apply it to our test set. I can show you the configuration window of this node again. So important here is to select the departure delay column and to uncheck this checkbox, skip nominal columns without domain information. All the other settings, I didn't change anything for now. Okay, next I will apply the decision tree which we trained to our test set. And this is something I can do in KNIME with the decision tree predictor node. So I create a decision tree predictor node. Into this one, I feed now on one hand our trained tree, and on the other hand, the test set. And now I can execute also this node. And this node appends now one additional column to my data set with the predictions. And what we see so I open now the output, we see we have now one additional column right on the right with the predictions. And what we see here is now that we have some missing values, and that's because I forgot to set one of the settings which are recommended in the annotation box, which is the setting for the no-truth-child strategy. The no-truth-child strategy is if we have an input feature and we make a split on this input feature, and we have now values in our training set, in our test set, which are not in our training set, then we have the problem that we don't have a branch for this one. And then KNIME predicts the missing value with the default settings of the decision tree learner node. But we can change this by going into the second tab of the decision tree learner node, into the PMML settings, and just change this to return last prediction. Then we just go to the subset before the split where we don't have a matching branch, and we just take the majority class here. And then I can execute it again. And then the next step is to evaluate our model. And that's something we can do with the scorer node. So I can look for the scorer node in the node repository. And then I go into the configuration window of the scorer node by double-clicking on the node. And the scorer node now evaluates how often was our prediction correct and how often was it wrong, and calculates some statistics for us. Therefore, we have to define in the configuration window in which column we have actually our true values and where we have our predicted values. So for the first column, I select the column where we have our true values, which is departure delay. And for the second column, we select the column prediction departure delay. And now this node can compare how often was the prediction right and how often was it wrong, and can give us some statistics like the accuracy, the Cohen's kappa, or show us the confusion metrics. So I click OK now, and then I right-click on the node, and I say execute and open view. Then I can see here now, in this view of the node, if you have selected execute and without open view, you can open this view by right-clicking and say view confusion metrics. We see here on one hand the confusion metrics, and on the other hand, we see here our accuracy, which is quite low at the moment with 62%. As well, we can see here the Cohen's kappa or the error rate. We have also an option in KNIME Analytics platform to see the tree which we actually learned. And therefore, I go back to the decision tree learner node. To see the tree, so the different rules the algorithm came up with, we can right-click on the decision tree learner node and then select view decision tree view. And here we see now that the first splitting feature that was used by the algorithm is the tail number, where we have a lot of different input features, or we have a lot of different features, and therefore we ended up with a lot of different subsets, which are actually quite small. And I can change this again by going back into the configuration window of my decision tree learner node, and I can change some settings because this is not really a good model. And if I go now back into my decision tree learner node and I change the quality measure from Gini index to gain ratio, and I train again, then I will see that I will get actually a better tree, and we will see this also in the performance of our model in a second. I will open this one because the gain ratio is much better, or it rather selects feature with less different values so that we have splits with less different branches compared to the Gini index. And that's why changing the setting can improve our model here. So for example, here we use now the departure time, where we split into only 2 subsets with the first split. And then checking whether the departure time is bigger or lower than 2237.5, we get already a nearly pure subset here on this side. And on this side, it's not pure yet, but we can make further splits here. And by clicking on this plus, we can see the next split is again done based on the departure time. And at some point, the model uses, for example, the planned departure time. Let's execute our model now. Let's apply this new decision tree also to our test set and see how good this model performs by just changing the quality measure which we used. And here we see now we get a much better performing model because we have now an accuracy of 89%. And you could try now to improve this model even more by changing more of the algorithm settings. For example, by applying pruning or not applying pruning, or by increasing this minimum number of records per node to avoid overfitting. Another option to evaluate how good your model performs is the ROC curve. And next, I want to use the ROC curve node to evaluate our decision tree. And therefore, I go to the node repository again on the lower left, and I look for the ROC curve node. Sorry about this. So I take the ROC curve from the JavaScript category, and I connect it to my decision tree predictor node. What we need for the ROC curve is not only the predicted value, but we need also the class probabilities for the different classes. Therefore, we go back into the decision tree predictor node. And by double-clicking on the node, I open the configuration window. And here I have now a checkbox, which is called Append columns with normalized class distribution. And this, by activating this checkbox, the node will not append only one column, but it will append now 3 columns for us, one with the prediction, and one with the probability for delay, and one for the probability no delay. So if I click now OK, and I execute this node, and we look at the output table, I open the output table, right-click, and selecting the last option. If I scroll now all the way to the right, we see here on one hand our new column with the predictions, but we see also, in addition, 2 other columns which give us the probability for the different classes, delay and no delay. And this information we need for the ROC curve. Then let's go into the ROC curve node. In the ROC curve, the information that we need is on one hand our true values, which we have to select here for the class column. So I select here departure delay. And then we can select one of the 2 classes as the positive class. And for this positive class, we also need the probability information. Therefore, I can exclude first all columns here in the lower part by just clicking on the button on the lowest button with the 2 arrows to the left. And then I can check for my column with the probabilities for departure delay being equal to no delay. And I can add this back in by just double-clicking on this departure delay equal to no delay. So that in the end, the configurations look like this. We have here selected the column with our true values. We have selected here one of the 2 values as the positive class. And we have in the include frame only the column with the probabilities for the positive class. And now the ROC curve node compares for different thresholds how good now the node calculates the true positive and the false positive rate for different thresholds. This means for the threshold of 0.1, 0.2, 0.3, and so on, for the probabilities to decide whether something is predicted as delay or no delay, and plots this for us in a line chart. So let's say OK, and execute an open view. Then we can see here the ROC curve for our decision tree model. And now to evaluate how good does our model perform, we can check 2 things in the ROC curve. One is that we can check the area under the curve. The best model would have an area under the curve of 1. A model that just selects randomly between the 2 classes would have an area under the curve of 0.5. And this means the best ROC curve would look like this, that our model goes straight up to 1 and then all the way to the right. That would give us an area under the curve of 1. But in general, a model performs better the steeper it is here in the beginning. And then I can close this window. The next part of our exercise is that we now, on one hand, save our model into a cell, and we extract the accuracy. Then we want to combine this information, and we want to output it here as our output port, because we want to do the same afterwards for 3 more models. And then we want to automatically select the model which performs best based on the accuracy of the model. So let's save our model to a cell, our trained decision tree, by using the model to cell node. So I can look for the model to cell node in the node repository. To save my model, which I have trained here, in a cell in a table. The other thing we want to do is we want to extract the accuracy information. And I showed you the accuracy information already here in the view of the scorer node. But the scorer node has also 2 output tables. And the lower output table, if I open this one by right-clicking and selecting accuracy statistics, we can see here that in this table, we have also the accuracy information in a table. And we can use now a column filter node and a row filter node to extract only this information. This means I will use first a column filter node to extract only the column accuracy, and then I will use a row filter node to only extract the third row. So I can look for the column filter node, and here I can use now the workflow coach, which gives us always recommendation which node you might want to use next. And from here you have also the option to create nodes in the same way as from the node repository. So I can just drag and drop the column filter node behind the scorer node and connect it to the lower output port of the scorer node. Then I go into the configuration window, and here I want to exclude now all columns, and I only want to include the accuracy. So your configuration window should look like this, that you have excluded all columns and only include the accuracy. Then I click OK, and I can execute the column filter node. If I now check the output table, I will see that I have now only one column left. And the next thing I want to do is I want to remove these two columns. So I want to filter out some rows, these two rows, sorry. So I want to filter out some rows, and this is something I can do with the row filter node. And I will add now a row filter node from the workflow coach behind the column filter node and connect it to the output port of the column filter. Then I go into the configuration window of this row filter node, again by double-clicking on the node. And here in the configuration of the row filter node, we have now many options to define which rows we want to include or which rows we want to exclude. First of all, we have to always select a column based on which we want to filter our rows. In our case, that's easy because we have only one column, which is the accuracy column. Then we have here the option to define a pattern matching. For example, we could say we want to include all values where the value in the selected column is yes. We could also use a range checking where we define a lower and an upper bound. Or we can also say that we want to apply our row filtering only to missing values. And that's what we want to do. And then here on the left, we have the option to either say, now we want to include the rows with the missing values, or we want to exclude them. And in our case, we want to exclude them. This means our settings here are the column to test on its accuracy. We want to check whether we have a missing value in this row. And we want to exclude the rows where we have the matching attribute, so where we have the missing values. Another option would be to include rows by number and just say here, I just want to include row 3. That would be another option and would lead to the same results. Then I can say OK, and I can execute the node. If I now check my output table, I see I have a table with only one cell, which is the accuracy value for our decision tree. The last thing we want to do now is to collect the information, the model and the accuracy in one table. So at the moment we have it at two different output ports, here the row filter and here the model to cell. And the node which we want to use therefore is the column appender node. So I can look for the column appender node in the node repository. I see it actually also in the workflow coach, even better. And I can drag and drop the column appender node behind my row filter node and behind my scorer node. The column appender node actually only works if the row ID is the same for the two tables. And if I check now the row ID of the row filter node, the row ID is actually not row 0, but it's called overall. And I want to change this. And this is something I can do with the row ID node. So let's quickly use the row ID node before we use the column appender node. Here we go with the row ID node. And the row ID node, I will just execute with the default settings. We can use the row ID node to replace our row IDs with values that we have in one column. For example, if we have a data table with customer information, when we have a customer ID and we want to use this unique customer ID as row ID, then we could select here now the customer ID column and use the customer ID information as the row ID. But if I just execute it with the default values, then it will just create nice row IDs for me again, starting with row 0, row 1, row 2, and so on. So I execute this node now, and I feed into the column appender node now our accuracy and our model. And if I execute a column appender node now, and I look at the output table, I see I have now a table where I have the accuracy and the model information, or our model. And as we will create now a table like this, also for the logistic regression and the gradient boosted tree algorithm, and then we want to add this information, or we want to concatenate the information below each other, we want to add one more information to this table, and that's the algorithm which we use. Otherwise, afterwards, we will not know is this the accuracy for logistic regression, or is it the accuracy for gradient boosted trees? And therefore, I add one more column to this data table using the constant column value node. So I can look for the constant column value node in the node repository. Constant value column node. I connect it to the column appender node. And then I can go into the configuration again by double clicking on the node. And now I can select that I want to append a new column, which I call algorithm. So this is the column header that I define here. And then I can define here a value, and I want to add the name of the algorithm which we used, and this is decision tree. With the general idea of the constant value column node is to add a column to your data table with a constant value, or to replace the values in one of your columns with another constant value. So in our case, we don't want to replace a column, so we don't want to replace our accuracy and we don't want to replace our model, but we want to append a new column. We call it algorithm, and the value should be decision tree. And if I execute now, and I open the output table, I see I have now a table with 3 columns: the algorithm name, the model, and the accuracy. And that's what I feed into the output port of this meta node. So what did we do in this first part? We trained a decision tree with different settings, improved it by changing some of the settings. Then we evaluated our model using the Roc curve and the scorer node. And lastly, we extracted our model as well as the accuracy so that we can compare our model later with the other models which we are going to train, and then select automatically the best performing model. So I will save now, and I will go back to the main work, or to the mother workflow, and continue with our next model. But before I do so, are there any questions regarding the decision tree? If not, I go into the next meta node, which should be logistic regression. So I go also into this node. And here now the goal is to train a logistic regression to predict whether a flight is going to have a departure delay or not. And therefore, I can look for the logistic regression learner node, because remember, for each algorithm, we have always a learner node to train the model and then a predictor node to apply the model. And here I can use now the logistic regression learner node to train the model. I connect the training data with the logistic regression learner node, and then I go into the configuration window by double-clicking on the node. Now let's see what are the recommended settings. We, of course, want to train a model that predicts the departure delay, so the target column should be departure delay, and then I can use one of the 2 values as the reference category. Then we want to use as a solver not the stochastic average gradient, but we want to use the iteratively reweighted square algorithm. So I changed this here. And then we want to exclude some of the features, in this case, the tail number and the column dest, because there we have too many different nominal values. So I can look for the tail number, exclude this one, and I can look for the column destination, dest, and exclude also this one. This means now the settings for this node is that we want to train a logistic regression where the target information is in the column departure delay. We selected delay as the reference category, and we use the optimization algorithm iteratively reweighted least square to calculate the coefficients of our logistic regression model. Then I say OK, and I can execute the logistic regression learner node. Now the learner node applies the logistic regression algorithm to train our model. And this node has also 3 output ports. We have on one hand here our saved model, our trained model, and on the other hand, we have 2 data output ports. The one in the middle is the output port with the coefficients and the statistics, and the one on the bottom are some model and learning properties. If I go now into the coefficients and statistics, then we see here the coefficient for each input feature that we have. And if the input feature is a nominal feature, then we get for each possible value 1 coefficient. We didn't get any statistics here because the Fisher information matrix doesn't have a full rank, and therefore we can't calculate statistics. That's what the error message is here. Next, we can apply our model using the logistic regression predictor node. So we feed into this regression predictor node our trained model and our test set. And also here in the configuration window, we have the option to append columns with predicted probabilities. If we don't check this checkbox, then the node will add only 1 column to our data set, which is the prediction. If I check this checkbox because we want to create the ROC curve again, then we get 3 columns again, 1 with the predictions and 2 with the probabilities for our 2 classes. Then I say OK, and I can execute the node. Next, I'm a bit lazy. I could build now all the same workflow which we did build here again. But I will just copy this part and then change it a bit for the logistic regression. So I copied all these nodes. And now I feed into the scorer node the output of our logistic regression predictor node. And then I can execute the node, and we can see whether our logistic regression actually performs better than the decision tree. And we have here now an accuracy of 87%. I remember an accuracy of something with 60% for the Gini index. For the gain ratio, I think we had an even a little bit higher accuracy than this one. Then we perform the same steps as before. We can also use the ROC curve to evaluate the model by feeding our output of the logistic regression predictor node into the ROC curve. Let's check quickly in the configuration window that the settings are correctly. So we have selected the column with the true information as the class column. We selected one of the possible classes as the positive class. And here in the include column, we have only the probability for the class selected as positive class. So this looks all good. And I can execute the node, and then we can have a look at the ROC curve. And we see here the area under the curve, I think, is a bit smaller, and it's not so steep here in the beginning compared to the decision tree. Next, we want to save also this model to a cell. So I use again the model to cell node. And then we use the same combination of pre-processing node or cleaning data manipulation nodes in KNIME Analytics platform to extract the accuracy from our statistics table. This means we have here the column filter node to filter the column accuracy. We have here the row filter node to remove all rows with missing values. And then we append the model and the accuracy information to one table. Last thing we have to change is that we have to change the value at which we add with the constant value column node, because I copied this node from the decision tree, remember. And therefore I go into the configuration window and I say, now I don't want to add a column with the constant value decision tree, but I want to add a column with the constant value logistic regression. And then I can execute this workflow snippet by executing the last node. This will execute all the previous nodes as well. And if we look now at the output table, we see here we have now a table where we have the accuracy of the logistic regression model. And we know also that this is the accuracy for the logistic regression model because we have this additional column with the constant value logistic regression. And then we can feed this resulting table into our output port of the meta node. Then I close this tab and I just save again. Then, are there any questions regarding logistic regression before we continue with the gradient boosted tree model? If not, then I continue with the gradient boosted tree model. So I go into our third meta node here in this yellow annotation box and open it again by double clicking on it. Here in this meta node, we now want to train a gradient boosted tree model. This means we don't want to train one tree, but we want to train multiple trees, which are stacked on top of each other. And they always use the error of the tree before to improve the model. So this is the idea of this gradient boosting algorithm. For this, we have the gradient boosted tree learner and predictor node again in KNIME Analytics platform. So we have the gradient boost tree learner and the gradient boost tree predictor node. And now I feed into the gradient boost the learner tree node our training set. And you see here now the different setting options again in the configuration window. Of course, we have to select the target column. Then we can define which of the columns we want to include or exclude. Then we have here the option to limit the number of tree depths. So this means how many splits is each tree allowed to make. And we can decide how many trees we actually want to train. And we can now train this gradient boosted tree first with the default setting with a tree depth of 4. But I will show you in a second how you can build a so-called parameter optimization loop in KNIME Analytics platform to automatically train different gradient boosted tree models with different numbers for this tree depth. But let's go first with the default setting. Then I say OK, and we can execute this gradient boosted tree learner node to train our first gradient boosted tree. Then we can apply it again with the correct predictor node, so with the gradient boosted tree predictor node. And into this node, we feed on one hand our trained model and on the other hand the test set. Then I can execute also this one. Next, we want to evaluate our model. That's something we can do with the scorer node, remember. So I can look for the scorer node. And in the scorer node, I now have to select where I have my true values and where I have my predicted values so that the scorer node can evaluate how often were the predictions correct and how often were they wrong. So we have here departure delay where we have our true values and prediction departure delay where we have our predicted values. And if I execute and open the view now, I see that I have an accuracy of 87%. And now the question is, can we improve this accuracy by changing this the number of splits each tree is allowed to make? And one option would be, of course, now that I write down manually, okay, with a tree depth of 4, I get an accuracy of 87%. Then I change this value here manually to 5, and I execute the workflow again, and I check the accuracy, and I do the same for 6, and I do this all the time manually. Or the other option is to do this automatically in KNIME Analytics platform with a parameter optimization loop. And a loop in KNIME Analytics platform always needs a loop start and a loop end node. And then we execute the part in between in each iteration for different settings. This means we need now a parameter optimization loop start and a parameter optimization loop end node. And the part which we want to execute now multiple times is the part where we train our model, we apply our model, and then we evaluate our model. In the parameter optimization loop start node, we can define now which parameter values do we want to use to test our model for different settings. And we want to add here one new parameter, which I will call tree depth. And I want to check now values, for example, between 9 and 15. This means, and the step size for the parameter is 1, and it's an integer value. This means this parameter optimization loop now creates for us a flow variable, and flow variables are additional parameters that we can use in KNIME to override setting options in a configuration window. That's what we want to do in a second. And in one iteration, it will create a flow variable which is called tree depth, which has the value 9. In the second one, it will create a flow variable which is called tree depth with the value 10, and so on for all the different values that we define here, from the start value 1 to the stop value 15, with a step size of 1. This means 9, 10, 11, 12, 13, 14, 15, and so on. So here the settings are add a new parameter and then define a start and a stop value. I now used 9 to 15. You could also say you want to test between 5 and 20. This would mean that you need more iterations, and of course it also takes longer. If I execute this node now and we check the information at the output port, we see we don't have a data table here, but we have the different flow variables. And we see we have here now one flow variable, which is called tree depth, and the value is 9. And we want to use this flow variable now in the gradient boosted tree learner node to override the setting option, the default setting option for the tree depth. And therefore, we need the flow variable in the gradient boosted tree learner node. And actually, each node has hidden flow variable input and output ports on the upper left and right corner. You can make them also visible by right-clicking and saying show flow variable ports, but you can also use them by just connecting an output port of a flow variable with the upper left corner of a node. Now we have to go into the configuration window and actually define in the node that we don't want to use here the manual defined value, but we want to use the value of the flow variable, which changes in the different iterations. And therefore, we have to go into this flow variable tab here on the top. And here we have now a list of all the different setting options that you find in options and in advanced options. And here we have one, which is called max levels, which defines the maximum number of splits. And here we want to select our tree depth to override the value the manual defined value, which we defined here, always with the flow variable value in the current iteration. And then I can execute my learner and my predictor node and also evaluate the model. Then we have here the parameter optimization loop end node to close our loop. And here we can define which value do we want to optimize. And we want to optimize the accuracy. And therefore, we need a flow variable with the accuracy value. If I check now the output table of the scorer node and I go into the flow variable tab, I see that the scorer node actually also creates some flow variables, and one is the accuracy. And therefore, I can just connect the flow variable output port of the scorer node with the parameter optimization loop end node. And now this accuracy flow variable is available in my parameter optimization loop end node. And I can select here in the configuration window which of my flow variables I want to minimize or maximize. And I want to maximize the accuracy. This means I select here accuracy and then maximize. Then I say OK and execute. And now you will see that KNIME executes this workflow part multiple times. In our case, 9, 10, 11, 12, 13, 14, 15, 7 times, always with a different value for the number of splits each tree in our gradient boosted tree model is allowed to use. And once this loop is executed, we will have 2 output ports, one with the best parameters and one with all parameters. We can also check in which iteration we are at the moment by using the node monitor. So if I go to view node monitor, it will add here on the bottom right an additional view to our workspace. So you know already the KNIME Explorer, the node repository, the description, but we can add more views. And one of the views is this node monitor. And if I select here, show flow variables, and I select the node parameter optimization loop, I see that at the moment we are in iteration 4 and the tree depth was 13. Now we are in iteration 5, and the tree depth is 14. This means we have one more iteration to go afterwards. And then we will have the accuracy for our different gradient boosted tree models available here at the parameter optimization group. And then based on these values, we can decide which is the best performing model, or which is the setting option for the tree depth that leads to the best model. And we can extract this information, retrain our model, and then save it also to a table to extract it afterwards. So now we are nearly there. Maybe while the workflow is executing, I show you one more time the flow variable tab. So to control this value with a flow variable, what you have to do is to go into the flow variable tab and then select here for the max levels the flow variable which we created with the parameter optimization group start. Now we can look first at the lower output part, where we have the accuracy for all the different iterations. And we see, for example, the best accuracy or the best performing model we get with a tree depth of 14. On the other hand, if we check the first output port, we have only the parameters for the best performing model. So here we see the tree depth with 14 leads to the model with the highest accuracy. And you can not only optimize one parameter, but you could add here also new parameters, define again the start and the stop value and the step size, and then use it also to override settings in the gradient boosted tree planner. Next, what we want to do is we want to extract the information of the best performing model, or the parameters of the best performing model, and then retrain our model and create also a table where we have the accuracy, the model name, and the model itself. Therefore, we want to create now a flow variable with the value of the best performing model. And that's something we can do in KNIME with the table row to variable node. What the table row to variable node does is it takes an input table and it only looks at the first table and then the first row. And for each column, it will create one flow variable, and the flow variable value is the value in the first row. So I look for the table row to variable node. So here we have the table row to variable node, and I take as input the table with the best parameter, which creates now two flow variables for me for each column 1. And one of them is the tree depth with the value 14, which is the best performing model. Next, we want to retrain our algorithm and evaluate it, and therefore I will just copy the nodes which we used before, Control-C, and I move it to here. Then I don't need this one, so I can delete this one. I will use now also again in the gradient boosted tree learner node our flow variable to control the tree depth, and I feed into my gradient boosted tree learner node our training set, and into the predictor node our test set. Then I can check that I used the flow variable to override here the setting option, but that was copied correctly. We use the tree depth variable to control the tree depth. This means we train now an algorithm with the value 14 here instead of 4. And then I can execute the trainer node, and I make it bigger again for you. And the last thing we want to do now is, as I said, those are the same steps as we did for the other algorithms, that we want to extract the accuracy and save the model. And therefore I go back into the meta node of the decision tree, and I copy again this part where we extract the accuracy and we save the model to cell. Copy it here and move it behind the scorer node. So I feed into this one, into the column filter now, our statistics table, and my trained model into the model to cell node. Remember here what we do. If I check the output table of the scorer node, we have here a table where we have the accuracy information. And we now use the column filter node to extract only the column accuracy, and then the row filter node to delete all the rows with missing values. We unify our row ID, we append the accuracy information with the model, and then we create one new column where the constant value is now, of course, not decision tree, but gradient boosted. Okay, and then I can execute. And now we trained 3 different models, and we have the accuracy and the models always here at the output ports. And what we want to do next is we want to create now one table where we have all these values below each other. And then we want to select automatically the best performing model of the ones which we performed, and select this one and write it to save it, which we could then give to group 3, which works on the deployment today. And that's what we want to do now in this last meta node here. So I can open this meta node. We have a question in the chat whether we will share the solutions, and you can find the solutions in this tiny URL folder as well. As I said, to compare the overall accuracy automatically, we first want to bring all this information together in one table. This means we want to write the different rows below each other, and that's something that we can do in KNIME with the concatenate node. So I look for the concatenate node in the node repository. And here we see now something new in the concatenate node. We have these 3 dots. And these 3 dots, they allow us to add more ports, more input ports to this node. And as we want to write 3 tables below each other, we need one more port, and therefore I can click on these 3 dots and say add input port. And then I can feed my 3 tables into this concatenate node. Then I can execute the node. And here you see now in one table the accuracy of all the 3 different models which we trained. We have here the model saved in a cell and the algorithm. And now we automatically want to select the best one. And what we want to do therefore is we want to have the best performing model on the top in the first row. That's something we can do with the sorter node. Then we extract only the first row, and then we can extract this model information from the cell into a model and save the model. So let's start with sorting the table that we have the best performing model on the top. That's something we can do with the sorter node. And we want to sort descending based on the accuracy. Execute, and let's have a look at the output table. We'll see that we have now the best performing model, or the model with the highest accuracy, on the top, which is the gradient boosted tree model. Then we can use the row filter node to extract only the first row. So I connect the row filter node to the sorter node. And this time I say I want to include rows by number, and I say I only want to include the first row. This means the first and the last row is row number 1. Then I can execute. While the node is executing, there is another question in the chat whether there will be a recorded version of what I'm showing right now. And yes, we will upload also this part in the breakout room to YouTube afterwards. If I now check the output table of the row filter node, we see that we have now only the best performing model, or the model with the highest accuracy. And next I can use the cell to model node to extract my saved model, which I have saved in the cell, back into a model. In the configuration window, I have to select in which column do I actually have my model. And this is this port object. And then I can execute this node. So the model is now here available at the output port. And I can save my model with the model writer node. And here I can now define in the configuration window where I want to save my model, whether you want to save it to a special folder, to your desktop, or you have a folder where you save all your models. That's then up to you. Or we could save it and pass it on to group 3 of this workshop, of this Learnathon, who's using it to bring this model then into production. Are there any questions regarding what I showed now?
Excuse me, is it allowed to ask questions verbally, by voice?
Yes, you can ask.
So you use accuracy only, but not the Cohen's kappa, area under the curve, and other metrics.
Mm-hmm.
How we can take into account different parameters to optimize our choice of model and so on?
Yeah, so what you can do, of course, accuracy, as I also try to emphasize, it's just a model with the highest accuracy. That doesn't mean that it is the best performing model. If you want to use other quality measures, for example, what you could do is, if you have here the column filter, you could include also the Cohen's kappa in each of them. Then you would have here at the output port a table where you have not only the accuracy information, but also the Cohen's kappa. You could add also the area under the curve from the ROC curve, because here the output port of this ROC curve node gives you the area under the curve. So you could use another column appender node and add to this table also the area under the curve. And if you would do this for all the models that we train, so if you make these changes not only to the decision tree meta node, but also to the logistic regression and the gradient boosted tree meta node, then you would have here as output a table where you have the accuracy, the Cohen's kappa, and the area under the curve. And then you could sort by multiple columns in the sorter node and define how you actually want to define which is your best performing model.
Thank you.
You're welcome, Alexei.
Sorry, may I ask you something?
Yes. Stefan, can you maybe please remind me how much time I still have?
If I note correctly, 12 minutes.
12 minutes. Okay, good. Then we have time for some more questions. Thank you, Stefan.
Kathrin, thank you for a wonderful presentation and very quick building of workflow, which takes sometimes weeks, yeah, in a real life. What I am really curious about, let's imagine we have trained and optimized several models, several type of models on the same training data and validation data. Is there any way to combine them in one classifier by bugging, by white sums, or?
You mean to create an ensemble of?
Ensemble of, it's bugging, it's.
Yeah. There's an ensemble fusion node.
Because the best classifiers are the combination of all classifiers.
Yeah,
you know.
yeah. I think there is an ensemble fusion node which you can use for this task. If you send me a message afterwards, I can look for the different options. I know that it's possible to do it, for example, for different PMML models, but I find it hard to remember now. I think it's prediction fusion. But I can check, we can also check together for an example in the hub for this node. Go to hub.knime.com. That's where I always look for workflows if I want to do something or I want to see an example. And I think prediction fusion is one option. And here you see, for example, we have a workflow where we have two models, and we use first the predictor node of both models, then we join the information, and then you can use the prediction fusion node, which will then use the majority class. So this is similar to bagging the naive Bayes model and the SVM model here.
It's really hard to imagine how to take the majority between two, you know. In this case, it's a pot situation. You need at least 3, you know.
Yeah. Correct.
No, it's just a joke. Yeah, it's a
but
more strong illustration.
It also works with more models, but as I said, I haven't used this node often yet. And there is another option, but I have to check for it. And then if you send me a message after the afterwards, I'm happy to look it up for you and answer it. Or you can ask on the forum. Then I'm also happy to answer there.
Okay, thank you, Kathrin. Thank you for this wonderful presentation. I have to insist it again. Yeah.
Thank you. Okay, then we have more questions in the chat. One is, will it use the same model we created by reference in the SAL? Yes, so we use this SAL to model node, and the SAL to model node really writes here the model with all the trained parameters into a SAL. And if we use then the SAL to model node, then we write back the model with all the trained parameters into this model format in this model object, which we can then write with the model writer node. So here we don't just save the information, or we don't just have the information that this is a gradient boosted tree model, but we have the trained model here at the SAL.
Kathrin, I was wondering about how this is going to be deployed. I'm just curious because we're referencing only the learner nodes and the cell to model or model to cell with, you said, with the training data, right?
Yeah.
So when they are doing testing, they're gonna replace the training with testing, and then do the results of the model, but they're not gonna be going through all the exploration details that we did, right?
Yeah. So if you want to deploy the model, so normally what you do is you have some historical data that you can use to train your model. And we use the test set so that we can also check how good does the model actually perform on data where we know the true value, which the algorithm didn't see during training. So that's why we create a training and a test set. But then normally, of course, you want to apply your model also to new data, to data which is not labeled. So let's say to a flight which leaves tomorrow, so to a flight tomorrow, and you want to know whether this flight is going to be delayed or not. And then normally what you do is you would build a second workflow, which on one hand reads this trained model, which we trained on our historical data. And in addition, this workflow would read also your new data. And then you would use, again, a predictor node. So you wouldn't retrain the model because that's what we did now. You would just take the trained model and apply this trained model to your new data. So for example, to the flights tomorrow, or to other customers. If you trained a model for churn prediction, that really depends on your model or on your use case. And the different options, what kind of deployment workflows you can build, is something that we talked about in group 3 in this workshop today. And this will be also available afterwards on YouTube. So because you joined my group and you missed this part, you have the opportunity to watch also this part afterwards.
Yes, great. Thank you for clarifying. I was curious about the training aspect. Yes, thank you.
You're welcome. Are there any other questions? If not, then we have a second workflow actually for this group as well. And therefore I will open the second one, but as we have only 5 minutes left, I will open the solution of this one and I will walk you through the solution of this one for the optional steps. What we want to show you here is that you can not only use our own implementation of the algorithms, but we integrate also other libraries, and one of them is H2O, and H2O they provide algorithms which perform really well on big data sets. And to use H2O, what you have to do is you always have to start with an H2O local context. And H2O has another way of how they save data. Therefore, we have to transform our data table into an H2O frame before we can start using the algorithms from H2O. And that happens here in this table to H2O. And then we have, instead of using the implementation of the gradient boosting tree algorithm that we have in KNIME Analytics platform developed by our developers, we can also use the algorithm provided by H2O using the H2O gradient boosting machine learner node. And this allows us now to use the algorithm from H2O, but here we don't need to write code. We just can do it in the same way as building the algorithm, building the workflow using our own nodes or our own algorithms, where we have a configuration window where we can define the target column, which features we want to include, the number of levels for the trees, and so on. So you see, it looks and feels the same as using the algorithm implemented by KNIME itself. And what we do here is we don't train, again, only one gradient boosted machine model, but we train multiple using something that is called cross-validation. Therefore, we use a cross-validation loop. So again, we have a loop start node and a loop end node. And we start with the cross-validation loop start node. And we then collect our results with the loop end. And the idea of cross-validation is to check whether the accuracy or the performance of our model depends on how we created our training and test set. And therefore, we train now multiple models on different training and test sets, where we take always another part of our full data set as the training set and the other one as the test set. Now I get a message that we have only 1 minute left, but that's okay. And in this case, we create 5 times a different training and a different test set. And we always train the model with the learner node and apply it with the predictor node, with the H2O classification predictor node. We evaluate our model with the H2O binomial scorer node. And then here at the output port, we have the error rate for the different iterations. Or here the error. And if this would be really different, depending on the accuracy, depending on the partitioning you made, then this would be not a really stable model.